Hello there, welcome to my channel on chemistry lessons. This is an A-level chemistry video and we're going to look at the nucleophilic substitution reactions of halogenoalkanes. So by the end of this video then, we're going to recall the use of curly arrows in mechanisms. We're going to outline the nucleophilic substitution mechanisms with haloalkanes using aqueous hydroxide, cyanide and ammonia as nucleophiles. First up though, if you don't subscribe, please do. Your support is very much appreciated and please take advantage of the likes and comments features. Let me know what we think. Right, some definitions to start with then, or some key information anyway. So the functional group in a halogenoalkane, sometimes called haloalkanes, is a carbon to X bond or a carbon X group, where X is something from group 7, so fluorine, chlorine, bromine, iodine. The nucleophile or a nucleophile is an electron pair donor. So if you were asked to define a nucleophile, you just say electron pair donor. And when we show a curly arrow, that's going to show the movement of a pair of electrons. Now, carbon halogen bonds are polar, and the bond polarity of a haloalkane decreases down the group. That's because electronegativity decreases down the group. So fluorine at the top is the most electronegative, so a carbon fluorine bond would be the most polar, all the way down to carbon iodine, which would be the least polar, but it is still polar. The term bond enthalpy is the energy required to break 1 mole of gaseous covalent bond, and it's the mean average energy required. As you go down the group, the bond length increases and the enthalpy decreases. So a carbon iodine bond is weaker than a carbon fluorine bond. And this means that haloalkanes get more reactive down the group. And that goes against other logic that you've learnt about halogens. So carbon iodide or iodohydrocarbons or iodo haloalkanes are the most reactive, not because they're the least polar or most polar, it's because the bond enthalpy between carbon and iodine is less, so that bond breaks more easily. So where does this fit on the whole reaction scheme then? Because these are all the reactions that we're going to learn about in A-level chemistry. So your haloalkanes then, tends to be your second topic after alkanes, and we're going to look at these 3 reactions. We're going to look at haloalkane to an alcohol, the haloalkane to a nitrile, and a haloalkane to an amine. This is what our specification says. So we're going to be looking at haloalkanes containing polar bonds. We've talked about that. We're going to focus on these 3 nucleophiles: hydroxide, cyanide, and ammonia. Just to remind you then that a nucleophile is an electron pair donor. So all 3 of these things, the hydroxide, the cyanide and the ammonia, they all have a pair of electrons that they are able to donate and act as a nucleophile. First up then, we're going to look at this haloalkane to an alcohol. And in this case, we need the hydroxide nucleophile. And the conditions would be aqueous. That is essential. I can't stress that enough, that it's aqueous conditions. It's in solution of water. Now, what happens here then? Let me draw an example of a haloalkane. Just going to draw a very simple one because all the chemistry happens at this CX bond. So this is where all the chemistry is going to happen. There's my polar bond. The halogen is more electronegative. I'm going to look at a hydroxide nucleophile. Hydroxide is OH-. Now I must show the lone pair on the oxygen because there's a lone pair on this oxygen, and we're going to show a curly arrow to show the movement of electrons. So what happens here is this pair of electrons on oxygen is donated to this carbon and a new bond is formed between the oxygen and the carbon. Now carbon can only have 4 bonds, so one of the other bonds has to give. And the bond that gives is this carbon halogen bond, and it kicks this out. Now, the easier that bond breaks, the more reactive the haloalkane, as mentioned earlier. So what will this produce? I'll be left with nothing happened to those 3 carbon hydrogen bonds, but there's a new bond formed now between the O and the H, so we've made an alcohol. And the bromine was kicked out as Br- because it took both the electrons from the bond, as shown by this curly arrow here. And that is the nucleophilic substitution mechanism for hydroxide aqueous with any haloalkane. Next up on this scheme then, haloalkane to a nitrile. And in order to do that, we need the cyanide nucleophile. So this time we're using cyanide, whether it's sodium cyanide or potassium cyanide, we don't mind. And this time it would be dissolved in some ethanol. And the nucleophile is going to be a cyanide nucleophile. So I'm going to draw my haloalkane again. I'll draw chloromethane this time. My nucleophile this time is cyanide, which is Cn-, but the minus charge is actually on the carbon. So I'm going to put the negative charge over on this carbon here, and the lone pair, it's a nucleophile. Now this is going to be exactly the same as the last one. 2 curly arrows like this, and we're left with nothing's happened to those 3 bonds, and we've now got this nitrile group. Now just to remind you that the nitrile group is in fact a C triple bonded to an N. That's what this nucleophile is here. It's a carbon triple bonded to a nitrogen with a negative charge and a lone pair, Cn. And we'll also be left with chloride. Now this product here is called ethane nitrile. You've made the carbon chain 1 longer. We've gone from chloromethane to ethane nitrile. So then the cyanide nucleophile is very good at making that carbon chain longer. So it's used quite a lot in industry. The third and final reaction then is this one here on the right. It's the haloalkane to an amine. And in order to do that, we're going to need the ammonia nucleophile. So this mechanism is a little bit more complex than the last one, because the last 2 were identical. So I'm going to draw another haloalkane here. I might go this time with fluoromethane. And I'm going to take ammonia. This time it's excess ammonia, that is important. And it's dissolved in ethanol and it's in a sealed container. So ammonia is NH3. And there's a lone pair on the nitrogen. I can put the lone pair on the top or the side, it doesn't matter, as long as it's on the nitrogen. So the first step is still the same. Let me draw this polar bond. The lone pair on the nitrogen attacks this delta plus positive carbon here, and then this bond breaks. You must be very clear with your curly arrows. Okay, so for example, this curly arrow goes from the lone pair, and that's essential. It must go from the lone pair, not just anywhere on the nitrogen. And it must very clearly go to the carbon, okay, not just near the carbon. And again, this curly arrow here must go from the bond to the fluorine. Has to be very, very clear. Managed to rub the bond out there. Okay, so what are we left with here? Well, nothing's changed here, but this time the nitrogen, because it wasn't a negative charge, and it's effectively donated an electron to the carbon to form a covalent bond, this nitrogen is now left with a positive charge. Notice how the other 2 nucleophiles had a negative charge, so when they formed that bond, they then became neutral. And fluoride has been kicked out. So this isn't quite finished, this mechanism. So what I'm going to do, because I know what comes next, I'm going to change this NH3 a little bit. I'm going to call it an NH2, and then I'm going to draw the bond to the H. So that's actually NH3, but I've drawn one of the NH bonds out. Because what happens now, and this is the idea of it being excess NH3, is another NH3 needs to come along, And this time the NH3, or the second NH3, acts as a base because it takes this H+. I'm going to have to do that arrow in yellow, sorry. So this second ammonia takes this H+, and then this NH bond, the electrons go back to the N to get rid of that positive charge. So the first NH3 over here acts as a nucleophile, and the second NH3 over here is acting as a base. So just to finish this off, what will my final product look like? It's just this CH3 with an NH2, methylamine. And we're left with ammonium NH4, and that will be ammonium fluoride in this case. Let's summarize what we've just seen then. So these are our three reactions that we've just looked at. We've looked at the haloalkane going to an alcohol, and in order for that to happen we needed a hydroxide, whether it was sodium hydroxide, potassium hydroxide, but the key point was it was aqueous. That was the condition was aqueous, and we heated it up. And that was a nucleophilic substitution mechanism. The second one we saw was the haloalkane to a nitrile, and that required sodium cyanide or potassium cyanide, and that was in ethanolic, and again we heated that up, and that was again an identical nucleophilic substitution mechanism. And the third and final one we saw was the nucleophilic substitution with ammonia, but this one was definitely slightly more complicated. So just remind yourself that that mechanism wasn't exactly the same, because the ammonia had two roles to play, which is why it needs to be in excess, or in this case I've said concentrated, and it was in ethanol, and that was also a nucleophilic substitution, but as we've seen it wasn't quite as straightforward as the previous two. And that's the end of this video then, so thanks for watching and good luck with your work.